everybody. So in this video segment, we will be looking at new capabilities in Design Hub. For this story, I will need three puzzle pieces. The first one is building predictive models. The second one is the automated generation of compounds. And the last one is assigning synthesis to external CROs. I will show you all puzzle pieces and a story where it kind of all clicks together. So let's get started. The first puzzle piece is building machine learning models. This is actually a very simple part because in the previous segment, you have seen that with the trainer engine now, we can really easily create high quality classification models, for instance, for permeability. So all we really have to do is make sure that everybody within the organization can use this new predictive model. So we go ahead and create a new tool within Design Hub for this permeability model. It looks like this. So you put in any virtual compound, and within a second or so, it gives you a permeability classification, 0 or a 1, and a confidence value, which is a probability value between 0 and 1. So let's take a look at the second puzzle piece, which is the automated generation of compounds. So many of you know about matched molecular pair analysis, which is used by medicinal chemists all over the world to analyze SAR within their projects. It's a really great tool because it can generate new compounds for us. It learns from knowledge bases which can help us prioritize transformations based on statistical data. And it can optimize against any data that we have. So any property of interest can be used here. However, so there is a con, which is that it requires a knowledge base. So only previously performed transformations can be suggested. So we thought about how to use MMP transformations as a way to suggest compounds within Design Hub. There is a really interesting data set, the Schur-Campbell data set, which is an automatically extracted list of about 20 million compounds pulled out from exemplified structures in patents. It has about 1.3 million patents and about 20 million compounds right now. And we have used an MMP learner to generate pairs of compounds. So these are pairs where around the common core or scaffold, there is one functional group which is different between the two compounds. So we have found about 40 million pairs using our MMP learner. And then we further analyzed what transformations these are. We have found about 1.4 million unique transformations, which is certainly a lot. So on the right, you can see a couple of examples, starting from a simple valence hydrogen to methyl transformation, which had more than 100,000 examples across this, but there are other really, really nice transformations as well in the data set. All of the groups have about 20 atoms at most, which is mainly due to the configuration of the MMP learner to consider only a certain maximum size. And with respect to the occurrence of transformations and frequent transformations, we have found that there's at least 50,000 unique transformations with about 50 or more examples behind them. And there is more than 1,000 transformations each with more than 1,000 occurrences between them. So this data set and the high frequency transformations suggest that we could actually have a compound suggestion tool which feeds on all of the published examples out there in the world. So puzzle piece number 2 is that we plugged this into Design Hub as well. So you put in any virtual compound, and within a couple of seconds, you get statistically ranked suggestions that transform your molecule. We also applied a second property to take a look at here to make sure that chemists can choose whether they want to shrink or increase the size of the molecules, which can be really, really helpful if you know that you have size constraints in a binding pocket, or if you want to grow more into a binding pocket, actually. So now let's take a look at our story And we will come back to puzzle piece number 3 in a minute. In a ubiquitin protease related project, we have 2 compounds. They both have one good and one bad property. So with one of the compounds, potency is good, but its permeability is poor. With the other compound, potency is good, but permeability is quite poor. So permeability is good. So our hypothesis and our question is whether we can create a compound that has both of these key properties optimized together. We will be using our new fancy permeability model that computational chemistry created for us. And we will be using our transformation library, our compound suggestion tool, to increase our options. So I will go ahead and log into Design Hub and finish drawing my compound. And on the right, you can see that we're able to describe it with many tools, including permeability and compound suggestions. And if I page through the compound suggestions, you can see that we have a number of results ranked by, for instance, mass. There's hundreds of them. So I will actually go ahead and save all of them without faffing them out too much. Just select all and save them. This takes about a second. So when we're done, we can switch over to our spreadsheet, which makes it a little bit more convenient to take a look at such a high number of compounds. In the spreadsheet, we have all of these compounds. They look just about all right. And some of the key MedChem descriptors are already calculated for them. So I will go ahead and run the permeability prediction on these compounds as well, which returns 2 columns. This binary classification of permeability and the confidence value. So I will set a filter for confidence, like 0.6, and sort all of the compounds with it. So this way, the high confidence permeability scores will be at the top. And the first 4 suggestions look kind of all right. So I will mark them for myself with a priority, just to make sure I can easily find it later. And because the rest of the compounds are also okay, I will go ahead and share these compounds so they have a unique virtual identifier. So this is how that looks like. The compounds I have IDs. It's pretty good. And we can start the discussion with our colleagues about resources. Resources bring me to the last puzzle piece. So in all MedChem projects, there is a question related to which compounds to make internally and externally. This is because both of these have advantages and disadvantages. So let's take a look at these a little bit. Internal synthesis certainly has the advantage of really efficient communication with colleagues and the use of all internal IT systems, which are super optimized for the team to work quickly. But internal synthesis, unfortunately, has the disadvantage that it's difficult to scale if one needs a large amount of capacity. External synthesis, however, can be easy to scale with the right contracts. It also provides access to special skills should we need them, and in some cases it can also be cheaper. Its big disadvantage, however, is the administrative burden which goes along with securely sharing just the right data. What is this data? So in a simple case, between the MedChem tools, the internal synthesis, and our corporate databases, project information, compounds, colleagues' names, priorities, details about the target and our compounds are all legally within the same system, same ownership. However, as soon as we introduce external parties into the system, we need firewalls. The current situation is the use of firewalls. Files and emails that transmit just parts of the information that we want to share, like which compounds we want to synthesize, with just the right person, telling them the amounts, the priorities, our comments and suggestions, and so on and so forth. And similarly, files are provided as the response about the compounds that were made. This external system, this external round, is what causes this high administrative burden. So we have taken a look at this problem and figured out a couple of really nice and secure IT solutions. This is split project access. The way it looks like in a couple of screenshots is that using our Kanban board and our single compound pages, we are able to differentiate between what internal users and external synthesis CROs can see. So both of them can use actually the same system. The internal user can track all of the compounds in the project in one place. So in our Kanban board, we can see who's working on what and what are the statuses and what are the priorities. And we can easily link compounds to hypotheses or chemical series in the project. On our single compound pages, we can see all of the details about this compound. If needed, we can access property predictions, like what you've seen a minute ago. And we have our discussion board where we can keep track with colleagues interested in the progression of these compounds. The external synthesis CRO uses this same system, but with a much more reduced view. They do not see the project. They do not see the chemical series. They do not see the scientific questions that we want to see answered. They only see the compounds that are assigned to them for synthesis. So there is a reduced view. The compounds are there with their virtual IDs, but not the scientific questions behind them anymore. The compounds with the data that we want to share are there, like the requested amounts and the purities and any special information related to shipping. But our internal classification models do not really show anymore. And the focus is on providing structured information to the designer of the compound, what amount we have been able to make, and what are the barcodes of the some of the vials, and what's the shipping label, you know. So we hope that with this system, if you should generate hundreds of compounds with possibly advantageous permeability and possibly great potency, you can easily access external synthesis CROs and benefit from a highly efficient system to keep track of all of this. That's it. That's my presentation. I hope you found something useful in it. If you have any questions, you know where to find us. Thank you.